Oh, you guys need to sit down. You need to sit down, friend. Sorry about that. If you guys could grab a seat, I'm getting pressured from a lot of different forces to make you guys sit down.
All right.
Do we have enough chairs? It'd be great if you guys could sit down. All right, perfect. Got quiet. Can we start? Okay. Wait, who said that? We're going to start. Cool. All right. Thank you so much for coming, everybody. For those that I didn't get to meet today, my name is Tom Nakata. I'm the co-founder and CEO of Qlay. We're the host of the event. Normally, I don't do the door. Normally, you have an intern, but the intern went back to high school because summer vacation ended. So I had to do the check-in today. But it was nice because I got to talk to every one of you, which doesn't normally happen. Oh shit, sorry. In the wrong order. Just before we jump into the content, I just wanted to quickly introduce what we do at our company, Qlay. We're hiring AI things. We do anything hiring and AI related. The two founders are me on the left and the guy who's doing the live streaming in the door in the back, Toku. Is an interesting person. I'm more of a consulting background. He's more of an engineering background. So the two co-founders, there's like the team's like 20-ish right now. What we do is we're building an AI proctor that catches AI cheating during interviews. I think you all know what goes on when you're doing online meetings and online interviews. They're using ChatGPT to generate answers during interviews. Online interviews aren't really effective anymore. We built a proctor to catch people doing AI cheatings. So yeah, that's what we do. It's a mix of different things like eye gaze analysis, speech pattern analysis. We monitor what's on the keyboard whenever an interview is happening. So that's that. That's our main business. We also do something else, which is we run our own recruiting firm using that screening system. So we essentially have our own AI screening, automated screening processes. So we use that to find a lot of good engineers and then connect them to a lot of startups that come to our events. So I guess we have two businesses, one AI proctoring and one like engineer recruiting business. We do a lot of these events. We have an event tomorrow here, actually. This is more of design-oriented things. We have an AI product lead from YouTube, as well as other incredible designers. So that should be very interesting. We also have a startup pitch event in San Jose in September. So if you're a startup and want to pitch, please let us know. There might be some spots left. Yes, sponsors. Thank you. Thank you always for sponsors. We have Signaz and Quentin today. And maybe I will invite them on stage and they could talk a little bit about what they do. Is that you? All right. Everybody, please give a round of applause to our friend.
All right. Hey, everyone. My name is Gotham. I'm a growth engineer here at Signaz. And essentially, what we do is we're an open source observability platform. What is observability? Essentially, at this talk, right, we're going to be learning a lot of AI systems and AI frameworks, I guess, or applications. Um, what's really important is to be able to gain visibility on your service that's running, especially as the scale is increasing, especially as more users are using it. You want to know what's really happening under the hood. And that's where observability comes in, and specifically our product, Signos. What we are is we are completely built off of an open source standard called OpenTelemetry, which is very different from our competitors, which tend to require specific customizations or configurations into their specific data store. And this prevents the vendor lock-in. We're also very cost efficient, and because we're built off of OpenTelemetry, especially as your usage is increasing and scaling over time, the costs tend to be relatively minimal. We also support all three types of traces, logs, and metrics all in one unified platform, which is very unique. Doesn't really get offered much. And because our entire data is stored on ClickHouse, we get really fast and responsive queries, which really improves the developer experience. And lastly, we're completely customizable in our deployment schemes. So we're able to be deployed via self-hosted. So if you have the compute necessary or the resources necessary for that, you can go ahead and do that. As well as we support cloud hosting. So we have our own cloud platform. By the way, everything is open sourced. And yeah, a little bit about us.
Thank you for that. We also just have one other sponsor from Quentin. Is that you? Or do we have a representative from Quentin today? Okay, I guess not. I guess we're going to skip him. Yeah. Unfortunate that had to happen, but that is that. We also have another sponsor, which is an accelerator. This is more of a startup news. One of the sponsors today is an accelerator called Open Network Lab, called OnLab. They invest about $100,000 per startup. They pick 5 startups per program, and they run it twice a year. Their valuation is a lot better than other traditional startups around. We went through them as well. We love them, super helpful. This building is actually owned by the people who run this accelerator. So if you're interested and trying to raise your pre-seed, please let us know. I'd be more than happy to put you in touch with the Open Network Lab people. That's the last slide. That's it from me. This is just a little campaign we do at every event. We do 2 businesses, one being AI Proctor and the other one being the engineer recruiting stuff. If you book a demo for the engineer recruiting, we're doing a heavy discount for whoever needs the engineer hiring services. But that's that. Without further ado, maybe we can go into the first session, which is from Jaidev from Amazon Prime Videos. Jaidev, are you there? Hello, hello.
Yeah, I'm here.
All right. Hello. Maybe I'll turn my laptop around so you can see everyone who's here today. Yeah.
Everyone. Awesome.
Nice. That's awesome. Jaidev, can you say something? I want to check audio.
Everyone, can you hear me?
All right. Sounds good.
Awesome.
In that case, please give a round of applause to Jaidev, and we'll see what we. Thank you. Screen's yours.
Cool. Let me share my screen. Just making sure everyone can see that okay. Cool. All right, everyone. My name is Jaidev. I am an applied scientist at Amazon at Prime Video. And today's talk, I'm gonna just give an overview of trends I see in how search and rexes have evolved in the age of LLMs and generative AI. And I think these fields are very, very intertwined. as AI agents and generative AI use cases sort of permeate the economy, the importance of strong search and rec systems will only increase. And on the flip side, with these new technologies, we can actually reimagine decades of search and rec sys research. So with that, let me get started. Quick intro about me. I studied computer science at Columbia, spent about 2 years at Microsoft AI as an applied scientist on the core search team, where I built ranking models for Bing recommendations and also for core Bing search ranking. I recently moved over to Prime Video, where I work on home feed ranking, both sequential recommendations and also exploring a couple of interesting ways we can use LLMs to improve our production system. I've also published papers at some of these search and Rexis conferences, and I was actually at KDD last week, and so some of this stuff is actually quite fresh, sort of top of mind. Here's a talk structure. So I'll talk first about one of my own papers. It's work we did back in 2023. And the reason I want to talk about it is the we actually never in this work we productionize using LLMs to improve quality of both retrieval and ranking at Bing recommendations, but we actually never use LLMs online. All of the compute is done offline, and I believe this is the most promising low-hanging fruit for um, most enterprises and most companies with ranking systems in production. So I'll spend some time talking about that paper and also on applications of LLM as a judge, and also for user understanding and user profile generation. We'll then talk about semantic IDs. This is a very new field. I think just a couple of years of research, with the seminal paper here published only in 2023, and then some production use cases of semantic IDs and generative recommendations. We'll switch gears to talk about AdLlama. It's a recent paper at Meta. And then I'll end with talking about how even though LLMs are extremely powerful as teacher models, wherever possible, always productionized, task-specific encoder models. And we'll end with some takeaways. Cool. So this section is LLMs for offline applications. I'll have a couple of slides that from my talk at KDD. This is our paper titled "Towards Web Skill Recommendations with LLMs." The surface of this deployment is a page-to-page recommendations feature. So you go to Bing, you get search results, and underneath the top few search results, you have this feature called Explore Further that is actually page-to-page. So it's both user agnostic and query agnostic. It only depends on this like triggering URL. So we call this URL 1. And these recommended URLs, we'll call them URL 2 going forward. The objective of this feature is actually to surface engaging exploratory web pages that may or may not satisfy the narrow intent of a user's query. Some of you may or may not know, but search is an extremely navigational application. So most queries that Bing gets or even Google gets, the vast majority of them are actually one-word navigational queries with very specific intent. So there is value in having a feature that surfaces more like exploratory things that user may want to see. The downside of not grounding this system in a query is that it can sort of evolve into clickbait, because without a query, if you're just training on user feedback logs, and people are sort of more likely to clickbaity, low relevance titles, your system will continually improve online engagement metrics like CTR, but you'll suffer in the quality of the product. And so a few years into this feature, we started getting a lot of quality DSATs. DSATs are when Bing users submit dissatisfaction reports. And the main categories here were like low relevance, clickbait, low authority. So you can see some examples here. The recommended web pages have nothing to do with the triggering URL, but is just sensational titles that people may click. So this was back in 2023. We had GPT-4 internally access to the model, as well as the model log probabilities. And I just want to preface this by saying when you're developing a retrieval and ranking system, you already have let's ignore the case where you're starting off from scratch and it's like a completely cold start case, and you already have a deployed system in production. You already have lots of engagement logs to train with, and so it's not really useful to use LLMs to try to predict user engagement. Your existing system already does an extremely good job, and it's sort of impossible to ask an LLM off the shelf to predict user clicks. We know because we tried. But what you can do is use LLMs to collect features, to engineer features and collect training labels for things you don't have signals for. And in our case, we didn't really have a good way to scale quality labeling, aside from having humans do it, which is sort of too costly to do at our scale. And so we devised a prompt that we call reco-DCG to score a URL1, URL2, in terms of how good of a recommendation is URL2 for this URL1 along different dimensions. So topic relevance, authority, freshness, location appropriateness, and how spammy the page is. And we found that if you evaluate this on a blind human labeled golden set, if you do careful prompt engineering and do chain of thought reasoning, you can actually predict user preferences, user quality preferences really well. And so this table shows that we can achieve 0.87 pairwise accuracy with, at the time, GPT-4 Turbo. So with that, we actually productionized the metric. We took that prompt and put it into a pipeline where you would scrape production, get for a bunch of triggering URLs, you would get recommendations, and in a A/B test, offline like A/B test sort of format, we would compute the DCG for a control and DCG for treatment. And so what this enabled for us is an extremely fast offline iteration on different quality improvement techniques. And I think this is one of the large promises of LLMs. You can get a very quick offline iteration loop, improving like experiment agility massively. Historically, pre-2023, if you worked at Bing, you would have to wait 2 weeks for you to submit a job, and then you'd have human labelers label them twice, and you'd get back results after 2 weeks, and then you said, oh, treatment has better relevance than control. Now you can do it in a matter of hours. So we shipped LLM as a judge as an offline metric, and that became a top line priority for the team. But now we have a prompt that is actually a very good predictor of recommendation quality. Why not use it to reach in the ranking system? So that's what we did. We used GPT-4 as a teacher model and collected dozens of millions of quality labels and used knowledge distillation to just train a very small BERT-like encoder model, which had magnitudes less parameters than GPT-4 Turbo. And this is what we deployed online. and eventually we would have like a we had this multitask student model that would predict click probability, recommendation quality, and we did a linear combination of these two scores to decide what the user will see in the top 5. So this is how we improved ranking system. We had some really strong quality gains. Shifting gears, you can do this for ranking, but what about retrieval? And since our use case was page to page, like doc to doc recommendations, we actually came up with a clever way to build a retrieval index completely offline. And the core idea was to do doc to query. So you have a web page, you can send it to any off-the-shelf LLM. LLMs are actually really good at using that web page and generating a bunch of 3 or 4 word queries about different aspects of the web page. For each of those queries, we can now go back to Bing, scrape Bing to get the top 10, and collect a bunch of documents and rank them by relevance and pick the top, say 30, and cache them offline. And so you can scale this pipeline to hundreds of millions. We actually scale it to, I think, 1 or 2 billion index, and build in a completely offline retrieval index that online all you have to do is just read off from this key value store. So we call this Q-recall, and we started off with GPT-4, but you can imagine for Bing, the web index is hundreds of billions of web pages, and for our feature, we wanted to have at least a 2 billion URL1 index supported by this new Q-recall, this new like LLM generated offline recall index. And if you just use GPT-4 to do this synthetic query inference is extremely slow. And so what we did is we just used a small language model. At the time, Mistral 7B was pretty performant, and did supervised fine-tuning with GPT-4 as generating the instruction response pairs, and Mistral 7B being fine-tuned. And you can see here for the same web page. So here it's this YouTube video of Adele's song. The Mistral 7B generated queries are on the right, and the original GPT-4 ones on the left. And with this, we were able to scale significantly more to larger index, achieving like a 60x throughput, if I remember correctly, on the same hardware, and keeping the quality of the web pages collected offline constant. One more twist on top of this is we also use implicit feedback to improve what queries that generated by GPT-4 are we going to let Mistral 7B see during supervised fine-tuning. And so we only kept the queries that got clicks, the more engaging queries. And this also gave us some sizable improvement in both online CTR and record ECG. And this is my last slide from this paper, just showing the production impact. We deployed this to production end-to-end. So both the ranking model, that multitask ranking model I talked about before, and the Q-recall were both deployed with both online CTR gains and quality gains. Record ECG is the offline quality. LLM is a judge quality metric I introduced. So this work at Bing was done back in 2023. Since then, there's been many follow-up works, many, I would say, even works in at the same time, people in the industry using LLM as a judge to build an offline metric that they use to iterate quickly on their models. And one recent paper from Spotify does exactly this, but for podcast recommendations. And so here you have a user, you have a user's historical podcast listening history. You can use that to generate a user profile, and then have humans judge the quality of the profile and the items recommended using that profile. And this is exactly what they did. They took a user's, I think the next, yeah, the next, I don't have, the paper doesn't have a example profile, but the LLM is fed a bunch of, is fed the user's historical listing history and is told to summarize what the content preferences, so what kinds of topics users interested in, as well as summarizing whether the user has an exploitative behavior style, or do they exploit and just listen to the same podcasters again and again, as well as summarizing listening habits, what time of the day they listen to what, and so on. And they collected a human labeled set of item and profile preferences, and they evaluated different techniques and found that the profile-aware LLM achieved sort of the highest performance when you ask it to uh, decide which of two ranked item lists are better. And I think the core takeaway here is not the specifics on how they prompted this LLM, but rather the fact that even for recommendation use cases, uh, generating user profiles and then using those user profiles in an LLM as a judge offline metric uh, gives practitioners and teams the ability to iterate a lot faster. As you can imagine here, the goal could be, let's deploy a much smaller small language model online to do batch inference of daily batch inference of users from their listening history and use that as an online ranking feature. This is similar to something that we did at Bing Web Search, where offline every day for tens of millions of frequent queries, along with the latitude longitude, we would generate a one paragraph query intent. And this is all done in a batch inference job daily, stored in a key value store, and online used as a feature into a more traditional encoder-like ranking model. So how do you in both of these in both of these applications, how do you decide if the user intent, or in this case the user profile, is good enough, where you have a LLM as a judge offline loop, which is what Spotify's paper talks about. I also want to mention this paper from Rex's last year that talks about user profile generation, but in a more end-to-end way. In Spotify's paper, it's really just like a human is like a scientist is just exploring with different prompting strategies to find what results in a good AUC score on their evaluation set. So it is sort of trial and error uh, prompt engineering. But what you could do instead is learn user profiles end to end, jointly trained with the downstream ranking model. So the objective here is, what is the best possible user profile I can generate when it's used as a feature to a downstream ranking model, provides the highest ranking performance. And quite literally, this is exactly what they do in a sort of generator discriminator fashion, where the generator is a large language model. It generates a user interest summary, and it's fed into a ranking model. In this case, I just used a two-tower embedding model, but it could be any ranking model. And the reward that the LLM gets that is then used for alignment is literally NDCG of this ranking model. And this paper also shows that the best performance is achieved when you train both the user profile generator and the ranking model jointly. And you end up with like very condensed but useful user profiles for ranking. I also, so we'll talk about semantic IDs and generative retrieval. And semantic IDs like I said, is a relatively new area of research. But the motivation for semantic IDs is that um, when I say traditional, even like deep learning based recommendation systems, they rely on random item ID and their associated embeddings. And so, for example, YouTube, every minute, like there's thousands of new videos being uploaded. Each of them just gets assigned a new random video ID that maps to its own randomly initialized embedding. But what happens in practice is that uh, for new items that enter YouTube, these randomly initialized item IDs generalize quite poorly. And so this is the essential quintessential cold start problem, which is quite an issue when you have a constantly updated item corpus like YouTube or Instacart or DoorDash and so on. And the core idea here is instead of just assigning a random ID to new items that enter the index, why not use a more semantically meaningful semantic ID? And these are not a single integer, but rather a string of a string of integers that are hierarchical in nature. I think this will make more sense on the next slide. But by replacing random IDs with semantic IDs and then asking a encoder decoder or a decoder model to just predict the next semantic ID that a user will watch, you can actually outperform some of the best sequential recommendation models. And YouTube actually put semantic IDs in generative retrieval in production. In practice, in theory, you can replace your retrieval and ranking stack with a single model that just predicts the next watched semantic ID or the next next purchase semantic ID of the item. But in practice, what actually works is you use generative retrieval as another candidate generator along with the existing ones that you have, such as two-tower embedding Bayes or sparse retrieval. And I think this
Jaidev, are you here? Oh no. Oh no. I think we have to cut it there. Do we give it a minute? Okay. Yeah. That would be a very bold move. Oh, Zoom crashed. Oh, no way.
Hey guys, can you hear me?
There you are. It crashed for a second.
There's actually a thunderstorm here in Houston. The lights went up. So yeah, hotspot.
Are you there or? Oh,
Yeah, can you guys see the screen?
yeah.
Okay, cool. All right. Yeah, so semantic IDs are hierarchical in nature. So in this example, you can see that the top level represents concepts like shoes, and so orange shoes and red shoes will both have the same top level ID, and it looks like color is the second layer here, and then the brand is probably the third one, and when you have large corpuses, these can be longer sequences of IDs, longer strings of sub IDs that represent a single item. And the task for a generative a recommender model is the author should predict what the next semantic ID will be. The way this is trained is you start off with embeddings of your entire corpus and do either hierarchical clustering or the Tiger paper from YouTube talks about RQVAE. I won't go into the details, but the general process is you start with your item descriptions, all the metadata you have embedded into embeddings, so hierarchical clustering, and assign hierarchically meaningful strings, case semantic IDs, and then train a sequential recommendation model. A good library to get started with with semantic IDs and generative retrieval is Grid. This was a KDD 2025 paper 2 weeks ago from Snapchat Research, and they, to my knowledge, are the only sort of well-written open source implementation of common semantic ID generation implementations, as well as generative recommender implementations. And they also have a lot of cool insights in their paper showing that simple quantizers is better than what YouTube proposed, and also how like encoder decoder architectures outperform decoder ones. And so encoder decoder architectures are ones where you feed in the sequence of semantic IDs interacted by a user into a encoder model, BERT-like encoder model, and with the representation learned after the encoder model that is fed then to the decoder that is tasked to do autoregressive prediction. And Grid shows that there's a lot of experiments that show that this is actually a very strong retrieval and ranking model. I do think running after I might slightly rush to the next couple of slides so I can get to the takeaways. But I did want to talk about AdLlama because this is a slightly different Rexis application. So the surface here is Ads Manager at Facebook, where advertisers can put in a sentence or two that describes the kind of ad they want, the ad text they want to see on their ad, and Meta generates a bunch of LLM generated recommendations on how to improve the ad text to get more engagement. And like what you could do is just like prompt, right? You can say make this ad text more engaging, but in practice, like you can actually do a lot better by aligning an LLM with real world feedback. And so that's what Meta's recent paper did. They call it RL from performance feedback, which is just a new new word for something quite simple, which is take a Bayes generation model, aka Llama 2, train a reward model that is trained to regress historical CTR. So for each ad and the ad metadata across multiple A/B tests, Meta can like pre-compute the historical CTR and train a reward model on this. So this reward model is capable of giving a reward that's proportional to how engaging that ad text is. And with that reward model now, you can just do a PPO and train an LLM to on pairwise data to choose always the more engaging text. And productionizing this PPO aligned Llama 2, they actually got single digit improvements in CTR, as well as double digit improvements in the number of ad variations created on the platform. So what that means is advertisers actually chose to generate more variants to do A/B tests compared to before, compared to the control. And this is the last section of my talk today, going into how crossing quarters, okay, yeah. Yeah, I can do it. Yeah. Um, I think I can just give the takeaway of this slide. And so the takeaway here is you can use powerful general purpose LLMs as teacher models and train significantly smaller BERT-like encoders on specific tasks. In this case, ReRank 2.5 is trained for instruction-aware ranking and achieve the same performance, but now enabling you to productionize with lower latency and lower cost. This is a good blog post on this. You can look at later. I also shared the slides, so I have to rush through this. And I'll end with some takeaways. And so, like I mentioned at the beginning, I believe the most promising and low-hanging applications of LLMs, when you're just starting off, in the search and rec space is to first develop an offline metric, aka LM as a judge, use them as teacher models and label generation for things that you don't have engagement logs for, and then subsequently deploy smaller task-specific models, and then for user understanding and user profile generation. Also, generative retrieval, which was a few years ago just a promising research direction, has now proven production gains in industry. Several papers at KDD and other conferences from industry, from folks in industry talking about production gains from using semantic IDs. And then I think the last thing I want to end with is that in a world where agentic and conversational recommendation interfaces will sort of arise and be deployed more and more, the core retrieval and ranking paradigms will now be tools, but this area of research is actually increasingly important, especially in a world where like there's more deep research workflows, agents, especially B2C ones, are getting way more personalized. Think ChatGPT memory. And I want to say, despite the fact that now we have long context, 1 million, 2 million size context windows, there are many, many applications where search and Rex's, this toolkit is extremely useful in conjunction with the core AI agent or the foundational model. All right, that's it. Thank you so much.
All right. Thank you so much, Jaidev, for joining us. We can't see you, but I hope you're okay in the thunderstorm, and we'll see you soon. Thanks, Jaidev.
All right, thank you, everyone.
Cool. Bye-bye. All right. Well, I hope I'm not. I hope my voice isn't too deep. I'll pitch it up a little bit. I think we can bring the next guest speaker. This one I'm particularly very, very excited about. We have Kriti Goyal from, I don't know what your comms teams allows me to say, but she works at a very big company. She does very exciting things there. I'll leave you to the introduction. Oh, you can't do mirror. All right. Well, Kriti, maybe you can introduce yourself.
Good evening, everyone. I'm Kriti, and this is Rajat. And let's start with a quick poll. So by a show of hands, how many of you believe that in robotics, there's going to be a ChatGPT moment? Oh, wow. Hold that thought, we'll circle back at the end. I saw more optimists than skeptics. So large language models and multimodal models like GPT, Claude, Gemini didn't just incrementally get better. They had an immediate phase change. Why? Data. They did it by feasting on an astronomical amount of internet data. And self-supervised learning algorithms turned this raw internet data into models that can reason, write, and create. But what about robots? Where is their internet of data? Where is the massively public available data sets of motor controls, joint angle, sensor signals? The simple answer is it doesn't exist. Robots live in the physical world, and the embodiment data is really the biggest bottleneck holding the industry back. The most common question people here have is, why don't we learn from the videos? Humans upload millions of hours of video on YouTube and TikTok every day. Videos of cooking, cleaning, assembling furniture, you name it. But in theory, this seems magical. In practice, this dream turns into two major obstacles. One, the grounding problem. How do you translate a human gracefully dicing an onion with the precision of joint rotations and gripper pressures for robotic arm? A person's movement in 2D cannot be replicated into a robot's 7-axis manipulator. The visual data is ungrounded from the physical commands needed to execute the task. And second is the perspective problem. Most videos are shot from a first-person or third-person perspective of human viewers and not for a robot's fixed camera arm. And while these two are not impossible problems, they are still exciting research frontiers, not ready for the industry to start working on. Okay, so if learning from human videos doesn't work, how about we just try simulation? And for decades, simulation has been the bottleneck of robotics R&D. Tools like NVIDIA, Isaac, Sim, Utility, and Mujoko let us train and test robotics in a perfectly simulated world. So here's a case study. Waymo actually published on their website that before they launched to the real world, they trained on 20 billion virtual miles in simulation. And this is what simulation gives you, the massive scale. The idea is really simple. If you can perfectly recreate an environment in simulation, you can use your robot on millions of scenarios for a fraction of the cost and time. But here's the problem. Robots is an art of the real world. The unexpected, the edge cases are necessary to handle. And the real world physics is messy. A simulation can model possibly a rain, but can it model how a street light reflects off a puddle into the camera's sensor and all of these weird edge cases? Can it simulate how a crumbled sheet of paper bounces off and the weird physics behind it? So 2021 study actually found that the number of driver disengagements of autonomous vehicles happened in that long chain scenarios. So now we move from simulation to the real world. But now we enter the lab. Every robotic startup begins here. So here's the problem. The lab is still a very sanitized version of the reality. A famous Stanford study from 2018 investigated this exact problem. They trained a robot to grasp common household objects. In the controlled lab environment, they achieved 96% grasp success. But when deployed into the messy real world, the success rate plummeted to 62%. This 34% drop is the difference between polished demo and a product that fails in my messy kitchen. So here's the takeaway. Lab data is the seed, not the harvest. It's where you start, but it's not where you can finish. This brings us to a newer, more exciting frontier, which is the synthetic data. Now, this is powered by generative AI and all of these models. So instead of a human programmer trying to hard code all of these edge cases, the Gen AI creatively puts it. A fantastic case study is from Wave. It's a UK-based AV startup. And they were trying to solve the problem of unpredictable pedestrian behavior of jaywalking. And they found that augmenting their training data with these rare synthetic jaywalking scenarios actually increased and improved the driving policy's reaction time by 12%. This is a huge deal, and it shows that we can use AI's imagination to cover critical real-world cases. But even generative AI has its limit. It struggles with the true messiness of the real world. So the takeaway here is synthetic expands coverage, but it still can't replace the lived chaos. So if simulation, labs, and synthetic data aren't enough, what's left? This is where Tesla flipped the equation. Their strategy was simple but radical. Deploy first, learn at scale. So instead of trying to solve everything in a lab, they built a data collection machine disguised as a car company. Their fleet of over 5 million vehicles act as massive distributed data gathering network. The cars don't just send back videos, they send back real-world steering, braking, acceleration traces linked to the video. This is motor-level, action-level data, the real deal, which we called embodied data in robotics. Tesla possesses an estimated 1.6 billion miles of driving data, and it generates this every month. With that scale, you don't need to simulate how a deer running across the road at dusk in the rain would look like. They can just wait for that to happen thousands of times, and then use data from the drivers who best avoided it to train their vehicles. So for self-driving, road data is plentiful. But what about humanoid robots in the kitchen? Data collection is harder, but the principle holds. Reality produces the richest data. This brings us to our hottest topic in robotics today, imitation learning, also known as learning from the demonstration. The idea has been around for decades, but the game changer was the diffusion policy. You've all seen what diffusion does for images with DALL-E and Sora. They start with random noise and iteratively refine it into coherent images by predicting a better version at each step. But what if instead of predicting pixels, you predicted a 7-dimension vector of joint angles for a robotic arm? This is exactly what diffusion policy does. This is a paper from Stanford which first released diffusion policy. So how do you train it? There are several ways. One is a human can physically guide the robotic arm into the right motion. They can use a joystick, they can use a VR control to sort of guide how they're doing it. And then the robot records every action, every angle, and every sensor reading while this is happening. If you do this enough, the diffusion model learns to generalize the policy from these demonstrations. Okay, another poll. For simple pick and place task, how many human demonstrations do you think it would take for a robot to learn the policy? Let's say under 100 and over 100 demonstrations. A study from MIT and Berkeley actually showed that robotics can learn to pick in place with about 50 demos using diffusion policy. And what's incredible is how fast this makes onboarding new tasks. Earlier, it used to be PhDs writing C++ code for several months. And now it can be a technician demonstrating it over an afternoon, and next day you can have your robotic pick up that task. But here's the catch. Imitation learning is still rough at the edges. The moment you show a slightly different cup or the position changes, the policy can fail. And now here comes reinforcement learning. So while imitation learning can give you a great starting point, reinforcement learning actually fixes the brittleness by allowing the robot to explore variations of the task on its own. It learns from that trial and error, getting small reward for actions that lead it closer to the goal. So why not just use RL from scratch? Because RL is notoriously inefficient. The search space is vast. So here's a very popular example, which is OpenAI's Dactyl, the robot hand that tried to solve robotics cube using only reinforcement learning from the beginning to end. It took 13,000 years of experience on simulation to be able to do it. This is completely impractical for almost any real-world application. So the secret sauce for most robotic startups is combining the two things, imitation learning and the reinforcement learning. The imitation learning from a small set of human demonstrations gets a great starting policy, which is 80% there. And then reinforcement learning is used to fine-tune around that policy and explore, and final 20% real-world edges. I don't know if I should say 20%, maybe next 18%, and 2% is still messy real world. Okay, now, so let's go back to my original question. After hearing all of this, how many of you still believe robotics will have its ChatGPT moment? Interesting. I see fewer hands there. And here's my view. Robotics won't have one single moment simply because it can't feast on the entire internet of data and make immediate use of it. Its revolution won't be overnight, but it's gradual, everyday micro moments learning. They won't learn to eat the entire internet in one gulp, but they'll snack their way through intelligence. It's still very interesting, so don't confuse incremental with boring. So in 2015, you'd have PhDs trying to teach robots how to fold laundry in several years. And in 2025, it's just technicians working over an afternoon and getting something similar. So here's the takeaway. The revolution is real, but it's granular and not sudden. Thank you. I'm here for any questions, and of course, Rajat is too.
You hear me? Okay. How do you draw the line between when imitation learning ends and wow, I'm blanking right now. And
The reinforcement learning. Do you want to take this?
So I think like imitation learning is very good if you want to, let's say, like pick up a cup 3 or 4 times. You can like make it work. But now let's say instead of a cup, you have like a wine glass. It's a completely different object. So I think basically you try it. You try the wine glass and see how it performs. And sometimes it works actually. But I think you find failures in edge cases. That's where RL can really help you, a lot more robust basically. Yes, yes. Yeah, exactly. So, yeah. It's more of an art than a science for sure. Certainly you're correct. Like I think an imitation is generally a little bit more deterministic. You know it'll work. RL is like hard, and like there's very few robotics companies that have really done RL in production. Imitation tends to be, it's possible, it's tractable today. RL is a little bit more still researchy. Yeah, I mean, I think it's like it kind of depends on how much like production you need to do. You need to do like hundreds of pick and place actions. IL is probably good enough. If you want to do millions and tens of millions and billions, then you probably need RL because you're going to see all the different edge cases. RL is really good for handling the edge cases.
I'm not a professional in this, but I would have assumed that that some of like the imitation would have taken place as humans that would wear like arm length gloves and it would track their movements, and then you translate that into like a 7-pivot movement, so the model knows how to translate that into how it can work. Would that be considered RL, or would that be considered imitation? And is that data points that you're using to feed in comparison to like a like a monitored video from a third person or first person perspective, or do you mix and match?
I think certainly people are mixing and matching, and for humanoids, I mean, like it's kind of like the body capture is actually people are doing that. I think a lot of robotics companies simply have like 2 separate robot arms, like 6-DoF or 7-DoF robot arms, in which like you take an HTC Vive controller, you take like something like a 6-DoF joystick, flying a plane, or maybe you even take another robot arm and you physically drive it around. It's just simpler. Those motion capture things are like very expensive and sometimes can be overkill.
Yeah, thanks a lot for this very interesting presentation. And my question is how far do you think from the robotics side that we're from AGI, and AGI meaning that we can really, without training, of course, the robot, you'd be able to, just like a human being. So how far do you guys predict that to be the case?
That was essentially the talk's topic. Forget AGI. It was like, do we even have a ChatGPT moment? I can give you the media answer, which is very exciting. And, this is just happening. A lot of companies are doing this. But if you actually look at talks from people who are doing this in practice, so Rajat runs a robotics startup called Chef Robotics. They would actually give very different answer.
Yeah, I think here's the reality. If you go to a lot of factories, you probably have the story that most factories are automated. And many are, to be clear. But there's actually millions of humans who are still working in factories, hundreds of millions around the world. So even factory jobs where you're essentially doing relatively redundant work is still really hard. Basically, the kinds of factories that are automated is like low mix. Like say you're doing like iPhones all day long, right? Like you have a line and it's just doing iPhones all day long. That's done. But imagine you're making food, for example. Well, there's like 300 different types of meals that everyone wants, right? Not just running iPhones this line, you're running pad thai, and then you're running a salad, then you're running like yogurt parfait. So like the variety makes it so that traditional automation doesn't work. And so those lines are actually just still humans. So there's a lot of that use case. So I guess my claim is that like, I don't know if really anyone knows, and if anyone tells you that they're lying, I don't think it's kind of like going to be this like you snap a finger, because it's just the physical world is well, it's a lot more. There's a lot more randomness. Physics is a lot harder than just like bits. Bits tend to be relatively deterministic. Physical world you have to deal with like a lot of stochasticity and randomness. Yeah. I think like here's the difference, right? For like let's say software engineering, right? There's like GitHub. You can train off of the internet basically. For like robotic data, like it is fundamentally more like incremental. Like pick up a laptop, you need to get imitation learning, and then to pick up a microphone, you need imitation learning. Pick up the chair, you need imitation. Like it's not just like you snap a finger. Like it literally is bound by the number of humans you have collecting the training data. You need a fleet of humans to collect training data. It's not just going to be you snap a finger and you get it. So I don't think it's going to be like all at once. I think it fundamentally has to be more like, maybe not like linearly scaling, but super linearly is hard, I think. That could be missing something. Like I guess my claim is like imitation and learning plus RL alone won't get you like, I don't think it will. I think there needs to be a bigger like maybe learning from video, right? Because that is a lot of data. That's a research area. I would argue IL plus RL is really good just to kind of get some robots into production, get started. But is it going to be the robot that can do thousands of different tasks in your house? Probably not. And maybe like one piece of context about this, imagine a house setting. It's not like you're just folding laundry all day long. You're maybe folding laundry for 10 minutes. But then you have to unfold the laundry, and you have to put the laundry in the washer, and you have to vacuum the floor, and you have to clean your toilet. Like, there's 1,000 tasks you're doing throughout the day. And if your robot can't do a lot of tasks, it's actually not that useful. They can do 1 or 2 tasks. Yeah, that's useful, but you're not going to pay 20, 30K for that. $500, $1,000, but you're not going to pay 20K, which is a very small bill of materials. Hard to make an ROI unless you can do all the tasks. But how do you do all the tasks without having training data? Well, that requires a lot of people. It's brittle right now. So that's not to be like doom and gloom. I just think it's not going to be like a snap of a finger like it was for digital AI.
Are we lacking accurate models of sensors and actuators, or is it the physical world? If it is actuators and sensors, can doing hardware in the loop kind of simulation get you better data?
Yeah, so I think sensors are pretty good. I think one of the big, at least the perception sensors are good. I think one of the big problems, though, is more proprioception. And what I mean by this is like, imagine you want to pick up like a water bottle, and it's like dark. It's like you can't see through the water bottle, right? Well, the human, you use perception, you use your eyes to figure out generally where do you grasp from, right? But then like you try to pick it, and you get some force feedback, and you're like, aha, it has water in it. That means I need to press a little bit harder. Whereas, by the way, if you try this, you can try this really quickly. Hands right now. Try to put like, if there's water in it, but you don't put enough force, you won't be able to. And that's kind of a general like problem, which is in robotics, sensors, but most of the sensors don't have force. Your finger has like all these sensors. Like, it doesn't exist for robotics. So basically, only are relying on camera data. Sensors like LiDAR, radar, time of flight. There's a bunch of sensors, but they're not usually force. And you can imagine using cameras only, but now as soon as you try to get close to the object. So I think there's some like hardware work that needs to happen. It's not just purely software. But as a general statement, a lot of the software is probably the core blocker. The software needs hardware to empower it too.
That's all for today, but we're there in the back if anybody has questions after. Sorry, thanks.
Sorry, I hate to be that guy, but I bear the job of a timekeeper. Last but not least, I think we have folks from all right, thank you so much. If you guys could connect this laptop. Last but not least, we have David Park, co-founder and CEO of Narada AI. Maybe should I introduce you? All right. I can do a little introduction of David. Is it working? So David's the co-founder and CEO of Narada AI. He leads the company's mission to revolutionize enterprise automation with large action models. He has bachelor's, master's, and PhD candidate in computer science from Stanford. So everyone, please give it up for David. It working? Oh, I see it. I see it.
Not sure if I even need this, but Dave Park, co-founder and CEO. And I think we're the last one. I wanted to introduce my colleague here, Fernando, who's head of our growth as well. But what we are trying to solve is a problem that everybody here probably knows about. AI tools suck in the enterprise. There's a host of AI assistants, co-pilots, Microsoft alone has probably 48 of them. And if you look at what they do very simple things within their own ecosystem. And if you look at why they designed AI that way, it's because the purpose of their AI is to sell more of their licensing, right? They want to sell their AI. They want to sell more licensing of Salesforce or Microsoft. But if you look at the real pain in the enterprise today, they're not simple tasks within one tool. It kind of sounds like this. I have to go into this portal, grab this data. Then I have to log into this other system and grab some other data, correlate that data, curate it, then spend 3 hours logging into yet another system, maybe an internal homegrown portal, and spend 3 hours manually updating data and fields in that system. Does that sound kind of familiar? It's this swivel chair problem of multiple disconnected systems, SAP, Salesforce, internal systems, spreadsheets. How do you make AI reason and actually orchestrate and execute across all these siloed systems? That's the problem we set out to solve. And recently, Harvard Business Review came out with a study. And they said the average knowledge worker today has to deal with 17 to 23 different systems and portals in any given week. More than 3 hours on average per day is wasted on manually navigating these portals, right? Salesforce, internal systems, SAP. But making AI reason about these systems and actually operate and execute across them is a very hard problem. So just a little bit about me, my background. I did my undergrad and PhD work at Stanford, started my first company, Coverity, out of research that we led into automated defect detection using compiler techniques. The reason why compilers is important, and I'll get there in a second, but essentially bootstrapped it, actually turned down every single VC term sheet, ultimately sold to Synopsys for close to 400 million. But this time around, I realized this problem was bigger. It's a harder problem. So instead of Stanford, I drove across the bay and teamed up with Berkeley because I wanted to build something and do something 100 times bigger than my first company. And right now, I know this is up for debate, but some of the biggest companies like Perplexity, Databricks, and some of the smartest talent is actually coming out of Berkeley. So I teamed up with a UC Berkeley AI professor, as well as a senior researcher out of the UC Berkeley AI labs, who drove a lot of the research into large action models, leveraging the LLM compiler technology that I'll talk about here in a second. And I teamed up with these very, very smart gentlemen, way smarter than me, to tackle this problem. How do you make AI reason across different systems and portals? And how do you make it do that with super high reliability? Not like even ChatGPT. Like my son uses ChatGPT to write his English papers. And everybody knows AI is inherently stochastic. It's gonna hallucinate, right? It cannot guarantee 100% accuracy. So what happens if there's slight hallucination on step 12 of a 30-step process? You're stuck. And that small little error, seemingly benign, is gonna compound and propagate as you complete that task. How do you make AI execute reliably? How do you build in unit testing and validation, guardrails, reflection, so that if there's any kind of error or exception that needs to be handled or hallucination, that you detect it and nip it in the bud before letting those errors compound? Third, we live in a world where in the enterprise, if everything was static and non-changing, then existing automation technologies like robotic process automation, the Zapiers of the world, if you will, they're going to be $1 trillion market, but they're not, because 99% of the enterprise world is dynamic. They're constantly changing, right? Interfaces are changing. Every implementation of SAP or ServiceNow or Salesforce, every company's instantiation of Salesforce is different. And even within that same company, the CIO can wake up one weekend and decide to change the layout of your opportunities page. And then suddenly all these hardwired, hard-coded bots and automations just break. And lastly, when we first started the company, before we actually raised any money, my co-founders and I literally did close to 1,000 customer calls with different enterprises to learn where the pain was. And most of these calls went like this. That we showed them our MVP. They're like, Dave, this is cool. This is great. Yeah, it's doing cool things. But let me show you something that my management will really open up their wallets for. And they would show us these back office, just like really messy, chaotic processes where most of those processes at some point in that chain involve some arcane homegrown portal that's been around for 10 years. It's going to be around for another 10 years. It has no APIs, no backend connectors. And so the only way to actually automate anything with that is to make AI mimic what a human being does. Logging in, navigating to the right page, hitting that drop down, filling out the fields. We needed to solve all these 4 problems to tackle this problem. And so, much like I did with my first company out of Stanford, leveraging compilers to essentially make a hard problem simpler, we did exactly the same thing with research out of the UC Berkeley AI labs. And by the way, it's the same lab that Databricks and Perplexity came out of, and the co-founder of both companies are our main and initial backers at Narada. And our research, and there's many papers that we presented at leading AI conferences in the last 2 years, like ICML, it started off with our LLM compiler. So much like 40, 50 years ago, compilers took higher level abstractions of code like C and Pascal and so on, and compiled it down into things that x86 architecture chips can execute very fast and reliably. We're applying the same methodology with our LLM compiler. So this time around, the input is natural language. You just describe in English what you need, right? Grab those invoices from my email, analyze that, and then can you please, update our ERP system with, the latest figures or something like that. Well, it takes natural language and it compiles it down into something that LLMs are very good at doing. So it takes very high-level, complex processes, breaks it down into many smaller steps, because the more granular you can get with these steps, break it down automatically, divide and conquer, is that each step can now be routed to an LLM that can do that one step very, very accurately. But more importantly, by essentially compiling it down into an intermediate representation that you can optimize for, you can basically build in unit testing and exception handling along the way. You can look at the dependencies of each of these steps and say, hey, steps 1 through 8, they're independent of each other. In that case, let's execute them in parallel. So much like compilers back 40 years ago, essentially compiled code down into something that can be optimized for accuracy and reliability and speed, we're doing the same thing with LLMs. And the beautiful thing about our LLM compiler is it gives us a framework to develop what we call a large action model. And the idea is this: without coding, scripting, configuration, not spending weeks learning something new, we're delivering almost like a ChatGPT-like experience, or even more simply, talking to your Siri on your iPhone. But now you can tell it to do grown-up things, right? And we take that input, natural language input, and we can actually work across all these frameworks. Some tools have APIs. There's growing, actually not as fast, but there's supposed to be growing support around MCPs. I think, Cisco is one of our large customers and partners, and they told me recently that even with all the hoopla around MCPs, there's only like 200 MCP servers actually in production today. Nothing. Companies have their own agents. They spent the past year spend millions of dollars building their own agents, right? But who's going to figure out what agent to call? And how are you going to actually coordinate those agents to actually accomplish real-world tasks? And then finally, just like I said, most of these processes involve some tool in that flow that has none of these things, has no APIs, has no agents, no MCP. So the only way to actually automate anything with that process, with that step or that tool, is through UI agents that can reason about these tools through the interface, understand it, and actually operate it much like teams of human beings would. And the beautiful thing about this is you don't have to worry about this. You don't have to sit there for months learning a new tool and pre-scripting all these steps, like step 3, call this API. Step 4, right, invoke this agent. You don't need to prescribe that. Why? Because as soon as you hard code something, it's going to work for 3 weeks and then break. Because we live in a world where everything's changing, requirements are changing, interfaces are changing. Our LLM compiler just completely abstracts that away. You just talk to it, and it will essentially figure out how to break that task down into many smaller steps using our LLM compiler technology, and it'll route it to the right API call. It'll basically do agent-to-agent coordination. And if all else fails, and there's no API or agents or MCP support, it'll invoke our UI agent to actually operate that step through the UI, through your web browser. Or in some cases, we have customers that have stuff still running on mainframes, right? There is no web browser, right? Or customers that have to actually operate through a virtual Citrix environment, right? Our UI agents are actually smart enough to operate that way. So enough talking about me. Let's just go straight to a demo to show you an example of how this works, especially our UI agent capability. And then I'll finish off with, I promise, just one more slide. And then I think we're done.
All right, let's see it in action, hopefully. Okay, so let's put everything that Dave said just into action. Oh, let me restart this. So like Dave said, we're focused on back office enterprise workflows, nasty, complex things, 18 different steps, 15 different tools, 10 days to actually do, but that we could bring it down into minutes, seconds, hours, depending on the workflow. But for this example specifically, right, we like to show this because a couple of these tools that we interact with, like Concur and Salesforce and HubSpot, don't like to play too nice in the sandbox, right? They don't have very robust APIs. So our orchestration layer, our LLM compiler, has to orchestrate these tasks in these tools through a couple different approaches, either through API function calling when they're available, or through front-end browser automation. So without further ado, something on the user interface. Just like ChatGPT, you can communicate with it as if it's your virtual assistant, just through natural language prompting. So in this knowledge worker use case, it's a side pane that lives on the right-hand side of your screen, where you can just input fields on the bottom right, and it'll take context from the left-hand side of the screen. So in this instance, I'm gonna ask Narada to upload this receipt to Concur and add myself and my teammate as attendees. So without further ado, I'll also stop it a couple times. So here it's calling the Concur agent, and it ran into a problem, right? Our LLM compiler ran into an issue. There's an exception, there's an error. I'm not logged in, or I'm sorry, I didn't specify which report to upload this to within Concur, right? So instead of hallucinating or breaking or guessing, our model will come back to the user, so have some sort of human in the loop perspective, then I'll give it more context, right? So if I wasn't logged into Salesforce Concur, same thing, it'll come back to me, I'll log in, and then it will go ahead and continue the workflow. I'll give it context here, Los Angeles trip, and everything is hands-off from here on out. It'll automate the browser as if a human was doing it, find the right buttons, find the right input fields, input the right input fields if they're not relying on each other in parallel, as you can notice with the speed, and even upload the receipt where it's available. And then since I asked it to add attendees as myself, it'll find the right button in the top center for attendees, and you can really notice the speed here. We'll go ahead and add myself and Lutfi as attendees as well. All of this is hands-off. All of this is through either our API function calling or through UI front-end browser automation. And we'll take every task 95% of the way, right? So we won't save anything, we won't send anything just yet. So that's how we could offer a high reliability, high success, and some security and privacy measures as well. In this example, I'm gonna upload a PDF receipt of a hotel and pretty much just ask it to do the same exact workflow, right? But the hotel receipt expenses are a little bit different than dinner receipts, right? You got to do the itemizations fill out some different input fields. Our model will just inherently and intuitively understand what's available through the receipt, the context, and fill out what's necessary based on the user interface of Concur. So same here with the itemizations. Going to find the right itemizations buttons. And in this case, the itemization input fields are below the scroll. So a lot of the browser automation that you guys might be seeing today out there only approaches automations through one model, through vision, right? So we actually do it through a multi-model approach through vision, HTML, and DOM reasoning. So our UI agents can see what's below the scroll. So find the itemization input fields that are below the scroll down there, and fill out the correct. Now, in this example, Salesforce doesn't play too nice in the sandbox regarding their APIs, right? So this is primarily all UI agents interacting and automating a task within Salesforce. I uploaded some notes from one of my meetings and then asked Narada just to upload the meeting notes to Salesforce as well as change the opportunity stage to meet and greet. So again, everything hands off here. Let the demo play. It's finding the meet and greet opportunity stage, clicking on it as I was doing it. Then I'm going to give the same prompt and ask it just to do it to HubSpot instead, right? HubSpot has different names for different things, different info fields. They call notes, I think, instead of call logs. So we'll go ahead and find the right buttons, find the right input field specific to HubSpot, and automate that task with it. Then at the end, I also asked it to upload the meeting notes, email it to my colleague Amir, our CTO. So instead of calling the HubSpot agent, it's going to delegate to a general agent and then write the email for me, open up that browser for Gmail, click on the right buttons, compose, and wait for me to send that. Yeah, that's my demo. Dave?
Awesome. Thanks, Fernando. Just to finish off this presentation. So, we are still working somewhat out of stealth, but at the same time, we're basically being used by some of the largest enterprises. In some cases through OEM, so you don't see us. So we have platform leaders in their respective spaces. So, like my thinking was this: when I was much younger, I had the energy to actually go sell directly to customers one by one. But now that I have gray hair and I have less energy, I said, look, I need leverage and scale. So instead of selling to one by one, why don't I just sell to one, and then one becomes many, in some cases thousands of enterprises. So many of the platform leaders in contact centers, collaboration, sales productivity, they tried building something like this themselves with big teams for the past year. It's hard. It did not work, right? Getting these things to about 60% of the way there is hard, but not that hard. But after that, getting to 80% reliability and robustness, 90%, and we have customers, even in the healthcare space, we're delivering 99.99% reliability. Right? It gets exponentially harder. So instead of trying to recreate the wheel, they're basically saying, hey, why don't we leverage Narada? We've done all the hard work. Starting 3 years ago, even before ChatGPT came out, we were working with enterprise customers and design partners on this, because you have to go to the back office and see what enterprises are doing, see where the edge cases are, see where the problems are. Because if you don't actually spend the time there where it's boring and not sexy, you're not going to know where are the problems, what are the problems, the edge cases that you need to solve. But for the past 3 years, we've actually been in the back office of these enterprises understanding how do you make AI so robust that it will self-learn and self-heal to changing interfaces? How do you make it deliver high accuracy and robustness, in some cases 99.99%, when just even getting AI to do something with one tool and getting it to 60% is difficult. And so right now, we are growing with enterprise customer revenue. We have large OEM deals. And some of the leading automation companies, some of the leading RPA companies as well, who have essentially tried everything under the sun. None of them work. They told us that everybody had great demos, but as soon as you try to actually deploy it in production, every one of them failed. They're actually leveraging us under the hood. And kind of one last thought to leave you with is the reason why we're succeeding is because we didn't try to boil the ocean, right? A lot of startups raised hundreds of millions, if not more, to build some kind of this big black box LLM that can work on all tools and all websites. And that's a fool's errand, because when you try to be everything to everybody, you're going to do kind of a half-baked job. It's not going to be very good, right, at everything. So for us, we focused on classes of enterprise tools that are heavily used across the enterprise. And the deeper you go into the enterprise, it becomes a lot more homogeneous, right? Like at the edge, there's like 10,000 different applications for like sales productivity. But as soon as you go deep into the enterprise, right, you look at systems like ERP systems, CRMs, invoicing systems, quoting systems, and so on. It's not like there's 10,000 of them. So we spend a lot of time on focusing. How do you make large action models that have a world understanding and have a very, very deep conception of how ERP systems work, how CRMs work, right? How collaboration tools work. And by the way, we never trained on any customer data from day one. And there's actually papers we wrote about this because we work with companies in healthcare. We like their data and their customers' data you cannot touch, right? And so we never trained on customer data from day one, but we were able to essentially infuse our models with the world knowledge of how these typical common enterprise tools in the back office work. And now we use self-learning and self-healing and self-adaptation so that when it goes into another customer, their instantiation of ERP, CRMs is going to look very, very different from the next customer, but we're actually able to self-learn and work without spending months of hiring an SIs to come in and actually configure and deploy. In some cases, we have projects where automation companies and SIs have spent 9 months trying to get it to work. It's not working. It took us a day and a half. It's actually working super reliably, comprehensively in this case, this was a large automotive company. And that's just the beginning. Like we're really compressing the time to deploy automations at scale. At the same time, the biggest problem in automation in the enterprise today is not the deployment, right? It's costly. You might spend a couple $1 million on actually configuring and deploying the automation. The real cost is cost of ownership, is maintenance. Year after year, because automations are hardwired and breaking, they're having to deal with downtime, having to bring in SIs to constantly fix these automations that are breaking all the time. And so what we've heard is that for every dollar that enterprises spend on deploying and configuring automation, they're spending $10 or more on maintenance and fixing and maintaining. So we're compressing the time to production, in some cases delivering automations at scale 20 to 50x faster, and we're dramatically lowering the cost of ownership because you don't have to bring in SIs every time some automation that's hard-coded fails. So happy to, I guess we're the last one. So we're around, happy to chat. If you've got a hard problem, we love hard problems. Come to us. We have a free POC model. We're so confident that we can actually leverage our large action models and LLM compiler to do it, is that we say, look, give us your hardest problem, and within a day or two, we'll give you a free POC. We'll show you actually showing Narada working in production or in test environments, automating these processes. Thank you.
Cool. David, is it okay if I get a picture with us and all the guests? Kriti, hey Kriti. Hey. Kriti. Oh, hey. Would you be able to come to the station? We can all take a quick picture real quick. And also, Jaidev's not here, so it's fine. Would have been great, but it is what it is. Okay. All right. Thanks, everybody. Have a good night. Stay safe.